Hello, my name is Dr. Maria Weber. I'm an assistant professor of physics at Delta State University, and today I'm going to go through some more calculations for the force table lab that my students were doing today in Physics 221. So for the lab that we're doing this week in physics, what I need from my students to turn in next week is something that we're calling a mini lab report. A mini lab report in this case has a table of your measurements. So I need a table that records all three masses that you used on the force table, and also gives me the angle at which those masses were hung on your force table. And so you needed to do that for 2 experiments. The first experiment was the instructions that you needed to follow on the index card, where you place 2 masses and you have a third mass, which you have to figure out where that mass is supposed to go and record the angle for that particular mass. And for the second experiment, what you needed to do was hang that third mass from the original experiment at 50 degrees on your force table, and then figure out at what angle you needed to hang 2 200-gram masses to balance out and make everything be in equilibrium. So be sure that you turn in 2 tables with measurements for each of those parts of the lab. So recording the masses and recording the angles at which you found experimentally for all of those forces to be balanced on the force table. Then the second part of the lab was to do the calculations that you do calculations to prove that the angles that you got for the masses in your experiment were correct. And then you needed to calculate the percent difference between what you measured in the lab and what you actually calculated to be the real value. We call the theoretical value with those calculations. So we took all the measurements in class today, and what I want to go through with you is an idea of how you want to go about doing your calculations for parts 1 and parts 2. So let's start first by drawing a free body diagram of all of the forces acting on your force table, okay? And so for the force table lab, all of the forces, which were the masses that you were hanging off of those strings, are in equilibrium, which means that the sum of those forces in both the x and the y direction has to equal to 0. So now let's draw a diagram of what your force table looked like. So here, this dot is the center of my force table. In the first part, in the first experiment we had you do, this first force would be pointing off at some angle. Let's say that that angle is about 30 degrees, and I'm going to call that angle theta 1. Okay? And the magnitude of this force vector, this force F1, the magnitude of it is equal to the mass of the object that you're hanging off of that string at that angle times gravity. So the weight of that object, its mass times gravity. And I suggest these masses were in grams, that you convert from grams to kilograms and take that mass, multiply it by 9.8 meters per second squared to get the weight, which is the magnitude of the force. Here I'm labeling one of these forces as F1. Okay, so this would be one of the forces that we asked you to hang one of the masses at a particular small angle of maybe about 30-degree angle on the force table. And then you had a second mass that we asked you to hang kind of in this quadrant down here. I'm going to call that angle theta 2, and I'm going to call this force F2, and I'm going to say that the magnitude of F2, the size of this force vector, is equal to the mass of that object that you were hanging on it on the string times gravity. Okay? And then you ended up finding a third vector, third force, that we're going to call F3. Okay? And so F3 was kind of pointing off in this direction here. Hopefully you found that you wanted to hang your mass F3. That was the additional mass that we asked you to hang. For most of you, it was a ball. For some of you, it may have been a cylinder with an extra little 50-gram weight on it. So that's what you have for your third force here. You should have found that you needed to hang it at about 160 degrees on your force table. So my positive x-axis over here, let's call that 0 degrees, okay? So this third force, F3, has a magnitude, that third object that you're hanging, times gravity. What we're trying to find in this calculation is what this angle, theta 3, should be. What should the angle be of the third force that you're hanging off of the table? And so I'm going to label it here as theta 3, okay? And yeah, the magnitude of that is the magnitude, is the mass of that object times gravity. So now what we need to do is we need to figure out the x and the y components of each of these individual forces. And then we're going to sum up the forces in the x direction and the forces in the y direction and set them equal to 0. So what we're going to want to do eventually is get an equation for the sum of the forces in the x direction equaling 0. So that's going to look like F1x plus F2x plus F3x equals 0. Okay? And so you also can do the same thing for y. The sum of the forces in the y direction has to equal 0. And so I'm going to have an equation for F1y plus F2y plus F3y equals 0. All right? So now, let's figure out what are the components of each of my forces in their x and y direction. So let's start with F1 over here. Okay? So I'm going to write the components of F1, the x and the y components of F1, I'm going to write them right here. So the x component of F1, I'm going to call F1x, is going to equal to the magnitude of F1. That's the mass for this first force times gravity. Okay? And multiply that by cosine theta 1. Okay, so the F1x, the magnitude of the first force in the x direction, is equal to mass times gravity of that first object times cosine of this angle theta 1. Okay, and the y component, F1y, is going to equal to the magnitude of force 1, mass 1 times gravity, sine theta 1. Okay? So we do the same thing for F2. I'm going to write that, I guess I'll write it just below here. It will look very similar. F2y is equal to the magnitude of F2 times cosine theta 2. Okay? And then the magnitude, oh sorry, I messed that up. The magnitude of F2x is equal to the magnitude of F2, which is its mass times gravity, times cosine theta 2, because we want the adjacent side here of this little triangle I could draw in. And so for F2y, this is going to equal to the magnitude of F2 times sine theta 2. Okay? So there we have the values for F1x, F1y, F2x, F2y. We can go ahead and plug in the numbers that we gave you on the index card for part 1 into these equations for F1x, F1y, F2x, F2y. And you can get the values for those. All right? But over here for F3y, we only know the mass times gravity of that object. And what we're trying to find in this calculation is what should theta 3 have been here, this angle right here. Okay? And so we're going to find an equation, a relationship for F3x and F3y. So F3 f3x is going to equal to the magnitude of F3, which is the third mass times gravity, times still cosine theta 3. Okay? And the magnitude of F3y is still going to be F3, magnitude of F3 times sine theta 3. Okay? So I'm just making sure that I've labeled all of these correctly now. F2x, we want the cosine because that's the adjacent side. F3x, we want the cosine, which is the adjacent side. F3y, we want the opposite side, so we use sine theta 3. But in some of these, I didn't take into account the fact that these vectors are actually pointing possibly in the negative x or negative y direction. So let's see here. So my force 1, F1, it has its vector with both positive x and y components. So we can leave these two components as positive here. For my F2x, or sorry, F2, my second force here, it is pointing in the positive x direction, so that's okay, but in the negative y direction. So here on my F2y, I need to actually make that minus the magnitude of F2, the second mass times gravity, times sine theta 2, this angle right in here. Okay? And for my F3x, I have this vector is pointing in the negative x direction, so I need a minus sign here on my F3x component. And the F3y component is positive, so I'm okay there. Okay, so now what I can do is set up an equation to solve for cosine theta by plugging in my values for F1x, F2x, and F3x. Right over here with my equation with the sum of the forces in the x direction equals 0. So I'm actually going to erase this Fy equation for now. Okay. So now for F1x here, you would have calculated an actual value for this. The first mass times gravity times cosine of this angle right here. So I'm just going to write this, I'll just write it as the magnitude of F1 cosine theta 1 plus, for F2x, we have the magnitude of F2 times cosine theta 2. Ooh, and I'm running out of room. Plus, here, the actually negative here, negative magnitude of F3 cosine theta 3. And that all has to equal to 0, right? And now we want to solve this equation for cosine of theta 3, right? So let's see here. If I want to do that, let me rearrange this equation. I'm going to move the F3 cosine theta 3 term to the other side of the equal sign. So I have the magnitude of F1 cosine theta 1 plus the magnitude of F2 cosine theta 2 equals the magnitude of F3 cosine theta 3. Okay? So I'm going to put a box around this equation right here. All right, and now I need to get rid of this F3 term, so I'm going to divide both sides by the magnitude of F3, which is the third mass times gravity. So then I'm going to end up with cosine theta 3 is equal to F1 magnitude cosine theta 1 plus F2 magnitude cosine theta 2 divided by the magnitude of F3. Okay? Then if I take the inverse cosine of this side, I will get my value for theta 3. Okay, so this is cosine theta 3 equals to this relationship. If I do theta 3 equals the inverse cosine of all of this side over here, then I'll find the value for theta 3. And you should find that theta 3 is approximately 20 degrees. Okay, very close to 20 degrees. So if I go back over here to my drawing, here I have theta 3. So the angle that we've just found in our calculation, let's write it like this, that's approximately 20 degrees, okay? And what you should have measured was an angle from the positive x-axis to your object that you're hanging off that we're considering to be mass 3. You should have found that angle to be about 160 degrees. And so 160 plus 20, that is 180. You go from positive x-axis all the way over to the negative x-axis. Okay, so you've measured this angle from positive x-axis to where the vector is. The way we did it, we just calculated the angle between the negative x-axis and our vector here. Okay, and so we've proven that this angle here is 20 degrees. If I subtract that from 180, I've got my 160 degrees that you took for your measurement. Okay, so all of that work and then getting the final answer here is showing all of this work to me, plugging in the values. That's what I want for you to show me for the calculations that I'm asking for this mini lab today. Okay?